I'm going to be talking about what constraints we can place on planet formation now that we have hundreds of multiple planet systems observed with Kepler. Okay, so I'll start with the solar nebular theory. Let's start from the beginning. This is the most widely accepted theory for the formation and evolution of our solar system. And so when you have a cloud, molecular cloud that collapses to form your protostar, you're often left with a disk of gas and dust surrounding the star. So it's from this disk that we form planets via accretion. And so the planet formation, to explain the planets in our solar system, are often described in three distinct but temporally overlapping stages. So in the early stage, you start with dust grains. The dust grains go through a sticking process where they grow into these planetesimals, and this stage is the most poorly understood phase, unfortunately, but we know that they somehow grow into planetesimals on the order of 1 to 10 kilometers. And numerical simulations have shown that you have these planetesimals in a swarm of dust and gas, and they continue to interact collisionally, and the gravitational cross-section is increased for the larger bodies, so the larger bodies grow faster than the smaller bodies. And then what you're left with is a disk with moon to Mars-sized bodies embedded in a swarm of smaller planetesimals. And so in the final stage, you have these embryos, and these also continue to interact collisionally and gravitationally until all of the material is accreted and planets are formed on stable orbits. So the time scales for all of these processes, and also if you look at the compositions of the inner terrestrial planets and the outer giant planets, support that the planets in our solar system were formed via in situ. This in situ model has been widely accepted. And what it means is these planets formed from material in their local region. So models of the solar system have often used n-body integrators to model the late stages of planet formation. They typically use a disk model that's based on this minimum mass solar nebula theory. And so what this is a protoplanetary disk that contains the minimum amount of solids necessary to build the planets in our solar system. So what planet formation theorists have done are to tweak the initial conditions to try to reproduce the planets in our solar system. And this minimum mass solar nebula, what you do is you take the planets in our solar system, you add enough light elements to bring them up to solar composition, and then you spread the mass out into a disk. And so it takes the functional power law form. And then it is from this surface density profile that you start your initial conditions for these n-body simulations. This model has worked well for the solar system. Here I show a typical simulation for growing for the late stages of accretion to form the terrestrial planets. So in this simulation, you can see the initial disk of moon to Mars-sized bodies. Each panel shows a snapshot in time for the simulation, and the eccentricity of the bodies are shown as a function of their distance to the star. So when you start the simulations within a million years, you start to get this dynamical excited disk. You get more frequent collisions, and they typically grow into stable orbits, roughly to planets that resemble our solar system planets in the order of 100 to 200 million of years. And so In this case, the simulation, we were trying to explore the distribution of water in the disk. We wanted to see if we could form water-rich planets in the habitable zone. So this is just an example. But you can see that if you start dry material at the inner disk and wet material in the outer disk, you get a lot of radial mixing, and it shows you the sorts of dynamics that you get from these simulations. Okay, so now we've spent decades, or not myself, but planet formation theorists have spent decades developing these models to try to figure out how our solar system, terrestrial planets, formed. Now that we have hundreds of multiple planet systems observed by Kepler, how do these models hold up? Kepler, we have hundreds of multiple planet systems. Most are compact systems. Most of the planets are super-Earth to sub-Neptune size. And giant planets appear to be scarce so far from what we found. So point being, there are a lot of systems that don't look like our solar system. And so another study that Sean Raymond did is to take the exercise of generating a minimum mass disk, but applying it to all of the Kepler multiple planet systems. And so what he found is that you can't make a universal minimum mass disk. Just with the different distributions of masses and architecture, it's so widely diverse that you end up with initial disks that have a wide range of masses, but also importantly, have a wide range of surface density profiles, a wide range of slopes. So having this wide initial conditions, can you still find a common mechanism to form these planets? And so first show an example of formation simulations we did for the Kepler 186 system. We announced the system earlier this year. It is a system of 5 planets, roughly Earth-sized, that orbit a smaller star. So it's another Kepler multiple planet system. In this case, all of the planets orbit within 130 days. So the disk is a smaller scale. They all orbit within the orbit of Mercury. And let's see. And okay, and so calculating a minimum mass disk for this system, what we did is we took all 5 planets and did a fit of the mass distribution, and then we also did it for the 4 inner planets because the 4 inner planets orbit within 22 days, and then you have Kepler 186f at 130 days. So we just wanted to see if we just extrapolated the disk from the inner planets, just to sample a range of initial conditions for the system. So here's one simulation of a disk around a star like Kepler 186. The star is a low mass star, about half the mass and half the size of the sun. And so what you'll notice here are the accretion timescales are a lot faster. There's a lot of mass that is closer to the star on shorter period orbits, so there's a lot more activity. But we're able to form planets that broadly resembled the planets that orbit Kepler 186. And so here is a figure that shows all of the planets that formed in our batches of simulations. The squares are the Kepler 186 planets, and then the open and shaded circle symbols showed the planets from the different initial mass, initial distribution of masses. And so what we found is that in order to form systems that look like Kepler 186, we needed to start with a lot of mass, with more than 10 Earth masses, and very close to the star, and with a very steep surface density profile. And so And when we did a lot more simulations, I'm not showing, where we varied the total disk mass range and other surface density profiles. And so this is what we found that we needed to reproduce these planets. Here's 2 sets of simulations that we did. The top show 10 simulations from one disk, and the bottom show 10 simulations from a second disk, and then you have Kepler 186 in the middle. With a steeper profile, we were able to form planets roughly similar in size to the Kepler 186 planets, but we would form too many. Below, with this other extreme disk, we were able to form planets that were similar in number, but then they're too large. So somewhere in there is a surface density profile where we can match them. So we can continue this exercise. But point being is that if you want to form these planets around the star, you need a lot of disk mass close to the star on a steep profile. So the problem with this is that these types of disks aren't commonly observed. You don't see this much mass close to the star. Another problem with in situ formation is that if they form in situ, then the planet architecture should reflect the initial distribution of material in the parent disk. So what you have, so if you were to match the final positions of the planets and look at the gas disks that would be needed to form those planets, you find in many cases there are models of gas disks that are inconsistent. The models of gas disks can only explain a narrow range of surface density profiles. And so if you believe these theories of gaseous disks and what we know from our observations, we can say that most known systems of hot super-Earths couldn't have formed predominantly via in situ. There has to be another mechanism. For Kepler 186 and some of the other multis, we believe that these planets were formed by some combination, probably some combination of having an early stage of accretion with an inward migration of embryos to increase the surface density. Probably this occurred when there was still gas in the disk, just enough to have them migrate inwards, and then followed by a stage of a late stage accretion. And so this seems to be the case if you want to match these models to what we observed so far. So right now we're currently modifying our N-body algorithms to include these types of gas drag. It's sort of a daunting task because these systems have a wide, huge parameter space to explore, but we still have these systems to compare to, so we're going to develop these models and try to see what types of gas disks and gas damping timescales and those sorts of parameters. We're going to start to study and fine-tune them and see if we can get a better, more universal model to form these systems of hot super-Earths. So that's it.
Sorry, maybe I misunderstood one thing. You assume that after the planets have formed, that they stay where they are, right? So basically, in order to derive the density profile in the disk from the planets that are observed, you have to assume that they basically, after they have formed, they stay where they are, right?
Oh, yes, like no late migration. Yeah. For these initial disks.
I have a question that may be silly. I'm not an expert on stellar planet formation, but on the plots you showed about the number of bodies and their size and their eccentricity over time, suddenly you don't have any small bodies at the end. Do you remove them from the plot, or don't you expect some asteroids, dwarf planets, or something?
Do you mean like these?
No, the grayscale one. After that, I think this one. After 1,000 years, you don't have any little body. Is that something you expect, or did you remove them from the plot not to pollute it?
So in this case, with having so much mass close to the star and having the accretion timescale shorter, all of the material was either accreted or dispersed into space. When you do these for different stars, you can have, if you have this disk around a single star, a sun-like star, like the ones I showed earlier, and don't put in a Jupiter, you can have trailing material for a long time. In some cases, if you have Jupiter analogs, you can have the planets form in the same time scale, but you'll have a lot of material that could come back and come back in like late heavy bombardments types of late stage hits. And so I think it depends on your star system that you're doing.
Okay, so we have time for last question at the back of the room.
Are there any general results about how large a fraction of the initial disk turns into planets? How much migrates into the star and how much is thrown out?
Yeah, we typically compute that. So I did so many just on the solar system before we started looking at we looked at Kepler 11 and the system. And in those cases, it did also depend on if you have another giant planet in the system. Having Jupiter definitely caused more material to be tossed into the star. So I can't tell you with this system, I didn't compute it, but actually I think with these, most of the planets were accreted. Less material went into the star, most of it just got ejected. I think around these low mass stars and short period orbits, the collision frequency, everything's more highly excited, it happens faster, the collisions happen faster, and then a lot of it gets tossed out. But we can compute that. I can't give you a general quantified answer for this case. But it can be done, I can talk to you later on.
Okay. No other question. Let's thank again Elisa.